Hello everyone, I'm José Luis Pontón, a master student from Universitat Politècnica de Catalunya, and I will present our paper AvatarGo, a plug-and-play solution for self-avatars in virtual reality. First, why do we want self-avatars? Having a virtual body synchronized with the user's movements can help to induce full body illusion and enhance some tasks. Some works present that synchronizing the virtual body can improve the exploration and interaction capabilities in VR. Full body avatars can also help users perform cooperative tasks more accurately and quickly. Also, if users can experience self contacts, it can significantly impact embodiment. Although self avatars can be done from an egocentric view using fisheye cameras, they can have problems when some parts of the body are occluded. On the other side, other works use sensors such as HTC trackers to capture information from the body and recreate the movement in a virtual avatar using inverse kinematics. However, assumptions are made regarding the offsets between the trackers and the avatar joints, and the user has to manually input some measurements to improve the quality of the movement. In AvatarGo, we focus on this second approach and try to solve the mentioned problems. Although full-body self-avatars provide some advantages as explained before, it is complicated to see an application using full-body avatars. If we look at some of the most played games in consumer-grade head-mounted displays, we can see that most of them use only a pair of hands to represent the self-avatar. In research, it may also be complicated and time-consuming to set up self-avatars for any VR application or experiment. That's why we decided to create AvatarGo. With a quick and easy setup, we can have self-avatars for any VR project. All devices are automatically identified and assigned. No specific orientation is required. We don't take manual measurements or adjust offsets per user. Although our implementation is in Unity, the focus of the paper and this presentation is to present the essential steps of AvatarGo so that it can be easily reproduced in any system. We use one head-mounted display with two controllers as usual in any VR application. Then we use one HTC tracker that provides information on the position of the hips. The other two trackers are placed on the feet. This position may suffer from jittering when the user is walking. However, it gives complete information on the orientation of the feet. Other solutions, such as placing the tracker on the ankle, might help reduce the jittering, but they have no information regarding the orientation of the feet. Any other hardware with similar characteristics could be used with the proposed method. However, our Unity implementation currently only supports SteamVR-based head-mounted displays with HTC trackers. Now I will present a summary of how the system works. The first step is only performed once, and it allows the developer to add custom avatars to their application. First, the developer selects an avatar and places it into Unity. The avatar should have a component that helps AvatarGo take automatic measurements and control several parts of the system, such as the inverse kinematics for the fingers. The essential step here is to input the height of the eyes of the virtual character and a sphere containing the head of the avatar for correct clipping when the user is in first-person view. Then, the developer adds the AvatarGo prefab into the scene. Several options can be selected. For instance, the avatar or how the hands of the avatar should interact with the controllers. These two steps are performed once, then the application is ready to be used. Now, when user enters VR, they have to stand in T-pose and press the trigger button. All devices will get correctly identified depending on their position. Next, the resized avatar appears, and the user performs the walk-in avatar step to compute the exact offsets. I will explain it more in detail in the following slides. After this step, the inverse kinematics is activated and the avatar is ready to be used. Therefore, once the application is set up, users can have self-avatars with two simple steps: a first calibration in T-pose and the walk-in avatar step. One of the problems when setting up full-body self-avatars is how to determine the offsets between the devices, such as controllers or trackers, to the joints of the virtual avatar. One solution is to assign manually depending on the user, or an average or fixed value. We call this method fixed offsets. For example, the root tracker placed on the back could be used directly to set the position of the hips joint. Or the position of the ankle used as an inverse kinematics end effector could be around 20 centimeters behind the foot tracker. But let's assume we have a user and an avatar with different body dimensions. The height doesn't match. The first thing we do is uniformly scale the virtual avatar based on the eye's height. We have this information from the calibration step using the head-mounted display position. However, this is not enough. We can see that the virtual avatar and user proportions are different. The avatar has longer legs. If we directly apply fixed offsets, this will happen. The hips joint position will be directly the hips tracker position. Feet and effectors will be determined by the feet trackers. The result is the inverse kinematics bending the legs of the virtual avatar to follow the end effectors. However, the user doesn't have the legs bent. In addition, the eye's height won't match either. Instead of using fixed offsets, we use the walking avatar step to compute exact offsets between some devices and their corresponding joints. With these offsets, the pose is preserved. Initially, the user and the avatar will be standing. The avatar will follow the movements as soon as the user starts bending the legs. The eye's height will be preserved. We use the walking avatar step to compute exact offsets. The idea is basically what I explained in the previous slides. Users choose an avatar and we perform a uniform scale based on the eye's height. Then the user has to enter inside the avatar as I'm doing in this video. Since the user and the avatar will be in the same pose, we compute all initial offsets. We ask users to place themselves until they feel their bodies are in the same position. We also display the devices as reference points since this helps locate the feet and other parts. Although not necessary, AvatarGo can also show a mirror to help users center themselves inside the virtual avatar. After the calibration, I will now explain how we perform the movement of the different parts of the body. Each part is treated differently since they have specific requirements depending on the position of the devices and other constraints. Let's start with the root or hips and the feet. Here we have 3 end effectors, the hips and one for each foot. These end effectors will determine the position of the corresponding joints, the hips and both ankles. In the walking avatar step, we compute the initial offset between the trackers and the joints. We also record the initial rotation of the trackers. With the following functions, we can find the position and the rotation of the end effectors at any frame. The idea here is that since we are storing the initial rotations and the offset, at any frame we can compute the difference in rotations to find how much the tracker rotated. This allows the system to work with an arbitrary initial rotation of the trackers. Once the positions and rotations of the end effectors are known, any inverse kinematic system can be applied. We use Unity's built-in AK for our Unity plugin due to its versatility and easy-to-use setup. For the head and back, during the walking avatar step, we store the vector going from the hips tracker to the head-mounted display. Then in runtime, we compute the angle between the initial vector and the current one. We apply this angle to the spine to bend the back. For the hands, we don't use any offset from the walking avatar step. It is enough to compute the end effectors so that the center of the controller will always appear under the palm. Once all end effectors are correctly positioned and the controller is under the palm of the virtual avatar, we apply a custom finger inverse kinematics to adjust the hand to the controller. Although we could have used a fixed hand pose for the fingers, we wanted to support different types of avatars with other skeletons and avoid creating different poses for each avatar. Instead, we developed a gradient descent solution that is fast and allows for multiple constraint optimization. We first represent the controller as the signed distance function of a capsule. That is, a function that, given a point, it returns the closest distance to the capsule, negative if it is inside. Then, for each joint of each finger, as shown here in red for the index finger, we can modify the rotation and numerically compute the gradient to minimize the signed distance function. To prevent the fingers from getting inside the capsule, we add a penalization factor and apply the absolute operator when the distance is negative. Other constraints can be used. For example, for our unit implementation, we also minimize the distance of the thumb to the plane intersecting the controller vertically through its center. This helps the thumb to be placed in a more natural position. To support a wide range of applications, we decided to have 3 modes for displaying the hands and the controllers. First, the controllers are always in their real positions, and the hands adjust to them using the fingers AK. When the avatar's arms are shorter, the controllers will appear floating, but the hands will adapt to them naturally. Second, the controllers remain attached to the hands. This ensures that the avatar always holds the controllers even when the arms can reach the actual position. And third, no controllers. Then we don't apply fingers AK. To evaluate our system, we conducted a pilot user study with 9 participants. We had 2 objectives here. 1, to evaluate the overall embodiment of the system, and 2, to evaluate to what extent our method for calculating exact offsets can enhance embodiment. For analyzing embodiment, we focus on agency and ownership, since users are always in first-person view and self-location is guaranteed. We perform a within-subject experiment with 2 conditions, F for fixed offsets and E for exact offsets. Then, each condition was tested first seeing only the virtual avatar and then seeing a semi-transparent overlaid avatar using the pass-through cameras of the head-mounted display. This allows the user to evaluate the self-avatar objectively. Then, for each condition, they perform 3 tasks. The arm task, that was while in T-pose, they were asked to move the controllers towards the body and then outwards. Second, the legs task, that was essentially to do squats. Finally, in the third task, users could try any movement. We asked 6 questions with scores ranging from 0 to 7. The first one was asked after the first task, the second one after the second, and the rest after the third. Full details of the results can be found in the paper, but I will summarize the main findings here. We used the non-parametric align rank transform ANOVA with contrast tests for pairwise comparisons. Users reported significantly higher embodiment for the avatar with exact offsets instead of having fixed offsets. This also happens when analyzing agency and ownership questions separately. Also, in all cases, embodiment was higher when using the virtual avatar than the overlaid one. As expected, users can see errors in the pose with the overlaid avatar that they don't perceive when using the virtual avatar. Since we also wanted to test the overall performance of the system, overall we can see that users reported high ratings of sense of embodiment for the avatar with exact offsets when using the virtual avatar. The median was 6 with an interquartile range of 1. We obtained the same results if comparing agency and ownership separately. To conclude, we presented AvatarGo, a simple and efficient system to have self-avatars in any VR application. The method can be implemented in any system, but we provide a Unity plugin that can be downloaded from GitHub. We provided a method to compute exact offsets to enhance embodiment. Also, a method for fast fingers AK, and the plugin incorporates collaborative capabilities. For future work, we would like to improve the compatibility with other VR systems and adjust the avatars to users better, not only perform a uniform scaling. Also, we would like to improve the AK or research motion synthesis methods for VR. Thank you for your attention.